So last time we covered exponentially weighted moving averages and how that relates to momentum specifically. Um, and over here, I told you about 0.9. This is, how much weight you're giving to the new value of the update. And this is how much weight you're giving to all of the stuff that we've seen before. And it could also be the reverse. It could be 0.1 times whatever the new update is, and 0.9 times whatever the culmination of the previous updates that we have, the running average. So now I want to tell you about something which is very, very similar, but it's called RMSProp. So one of the visualizations is this thing called a contour plot. And so it's really hard in 2D to be able to draw something like this. So instead of having something like this, we have let's say we're trying to represent a bowl, right? This is some kind of 3D bowl, and I'm really bad at drawing 3D stuff, right? But let's say that this is some kind of bowl. Instead of drawing this bowl, we can make it we can sort of let's say this was the bowl, right? We can draw this line, this circle around the center, right? This circle around the center, and then this circle around the center, and so on. And then look at that from the top. So that would correspond to, so this would be the circle in the center, like this, and then a bigger circle, right? And then a bigger circle, and so on and so forth, right? So that's the smallest circle that corresponds to this one. And then this biggest circle corresponds to the outer circle, let's say. So this is called a contour plot. And so I'll just be using that for a small demonstration right now. So for the contour plot, let's say, so this was the bowl, and this was the bowl example, and then let's say we're trying to go to the middle. But the thing is that the bowl is not completely a circle. It's not like a circle like this. This would be a contour plot if the thing was actually completely circular. But let's say it's instead skewed. So there's one axis that's kind of larger than the other. Okay, so at any given time, at any given point, let's say we're over here, right? And this corresponds, by the way, this corresponds to, um, W1, and this corresponds to W2. So two different weight parameters. And this is whatever the value of W1 is at this example, and this is the value of W2 wherever. At any given time, for this contour, basically the way to minimize the cost would be to go perpendicular to the contour. So you would go perpendicular to whatever the tangent line is here. And so this is just a fact in math, but basically you would go this way, right? And so let's say we go this way and we end up on this curve right here. And then we would go perpendicular to this line over here. So we would maybe go here, right? And then I'm assuming that, there's another contour that's like somewhere here. So it's going to be maybe somewhere here. And then from here, it'll be like this. And we'll just keep on going to the middle like that. But notice how we went this way and then we went this way, right? And so momentum would allow us to, like I said before, momentum would allow us to go, it would smoothen out this turn, right? But in this case, it might not be actually that great. What I wanted to tell you about was RMSProp, and the momentum might mess up here actually, because it might have us keep on going in this direction and then slowly turn in here, right? Just think about everything that is happening slowly. All of the direction changes are happening slowly in momentum, right? So if this is the direction that we're going in, then the turn is going to be very slow. Instead of very drastic from here to here, it's going to be very slow like that. And so we have this method called RMSProp to turn this image, which is an elongated like oval type shape, into something like this. Because if you consider anywhere that I'm over here, if I'm over here, let's say, and this is circular, it'll always point directly to the center. And so it'll be much, much faster in this case to optimize than this case where I have to go around and then to the center, right? Ideally, we would turn like instead of doing this, we would turn this into something like this, and then we would be able to go directly to the center, right? And so you can do this using RMSProp. The idea of RMSProp, or the rationale, is that W1 and W2 are on different scales, that they're not like all the same size, sort of. One might be on the scale of, like, W1 might be on the scale or around the value of, on the magnitude of 0.1, and let's say W2 is on the magnitude of 1, right? Meaning it's like, it's like 10 times bigger approximately than W1, right? And that's why this elongated circle thing is happening, or this oval thing is happening, right? And so what if we were to divide both of them by their respective magnitudes? So let's say that the magnitude approximately for this is 0.1, the magnitude for this is approximately 1. What if we divided by the magnitudes in each case? Then W1 gets transformed into W1 divided by 0.1, and W2 gets transformed into W2 divided by 1. And so this becomes 10 W1, and this becomes just W2. So 10 times W1 is the new feature, and then there's W2 as well. So you can think about it like we're kind of we're going to stretch this axis so that it's bigger, right? And the hypothesis is that if you stretch the axis to be bigger, then it'll become more like a circle. If you can think about like me extending the oval like this, it'll eventually become a circle. And so how do we do that using exponentially weighted moving averages? What we can do is we can have an exponentially weighted moving average of not the W's themselves, but the squares of W. Okay. So you have W 0 squared is we used V last time. TUV, let's say we use P. Okay. So for RMSProp, actually, can we use R? Maybe we'll use R, right? So for R0 could be equal to W0 squared, right? R1 is equal to 0.9, let's say, times R0. Sorry, not times R0, times W1 squared plus 0.1 times R0. So you're taking in the new signal, which in this case is not the weight itself, not W itself, but W squared at that time step. So in this case being W1 squared, and then times 0.9, that's the weightage that's being given to a W1 squared. And then you have 0.1 times everything that you've seen before, which is just R0. And then you have R2, which is 0.9 times W2 squared plus 0.1 times R1, and then so on and so forth, right? Dot, 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 all the way to Ri. What is the rule for Ri? You're taking in 0.9 weightage of Wi squared plus 0.1 times whatever was at the previous time step, Ri minus 1. If this is Ri, then this is Ri minus 1, right? So now you have an exponentially weighted moving average of the W squares, right? But what does W squared tell you? Note that W can be positive or negative, right? And so we square it as a sense of like how large it is in terms of a positive number, right? But in order to if you think about it, the absolute value of x for any number x, right, is always equal to x squared, and then you take the square root of that, right? If you take, let's say, -3 squared, and then you square root that, you'll get the positive value 3, right? Which is essentially the absolute value of -3. And if you have +3 squared, and you take the square root of that, then you get just 3. So that's also equal to the absolute value of 3. So the absolute value of anything is equal to that thing squared and then the square root of that. So the hypothesis, or like what we're trying to do, I guess, is collect a reasonable assumption for what is the magnitude overall of W, right? For that particular weight W. And the way that we're doing that is through an exponentially weighted moving average. Every time we're updating our sense of what is the magnitude of this weight, how large it is on the scale of, 10 to the power of -6? Is it on the scale of 10 to the power of -2, 10 to the power of -1, 10 to the power of +1, which would probably never happen, in my experience at least. Uh, and what is the magnitude? We're trying to update our sense of that at every single time step. And then what we're going to do is in our update, when we're updating it, so let's say this was our original update function. So this thing right here, we can scale that by the magnitude, right? So since over here, this update in this direction would correspond to something like this, right? And we want it to correspond to something like this, right? Which means that we want to shrink whatever this is, and we want to basically like point more in this direction, right? And because of that, what we can do is we can just divide this by we used r, right? So r I, and then square root that. So remember this w, so ri is approximately what is w squared, right? It's like answering the question of what is w squared approximately, right? But in order to get like the absolute value of w, we want to divide by the absolute value of w. Then we can divide by the square root of ri. And so this would give us RMSProp. And really quickly, we can just figure out what atom optimization is from here. Atom optimization. So for atom optimization, we take in momentum and we take in whatever RMSProp was that we just figured out about. So our new update is W equals W minus alpha times not dJdW, but whatever. So previously we had used the variable V, right? V is the exponentially weighted moving average of all of the dJdWs, right? So V I over the square root of Ri. And let's say this is, yep, so this should be correct, I think. Yeah. So if you have if you were trying to figure out the W for a particular time step, you use the value at the previous time step, you subtract alpha times VI, which is essentially our way of guessing what is the value of DJ dW. And this is divided by the square root of Ri, and Ri is our guess of what is W squared, right? And therefore the square root of that would just be the absolute value of W. So we're dividing this by the absolute value of W. And that is the parameter update for atom optimization. And it just depends on like what is your what is the number, the coefficient for um for these things over here. So are we using 0.9 over here? Are we using 0.1 over here? Are we using 0.999 over here? Right? 0.5, 0.7, whatever. So it depends on this, how quickly you update, how quickly you're turning, right, for momentum, or how much you're changing your sense of the scale of W by, and all of that depends on like this number itself. But generally speaking, atom optimization is characterized by this equation here. So thank you.